Hello, and welcome to another episode of ROBOTIS Talks, where today we're going to be speaking with Ground Control Robotics. I'd like to start off by introducing Daniel Soto, the CTO of Ground Control Robotics,
Hi, glad to be here.
and then Dan Goldman, the president of Ground Control Robotics,
Hello. Thanks for having us.
and then Eric Teeter, the media lead over at Ground Control Robotics. I don't know who'd like to step up to the plate for this one, but would you like to introduce to the audience a little bit about what you guys do over at Ground Control?
Yeah, why don't I step up as the most senior member of the call here? So I'm Dan Goldman. I'm a physics professor at Georgia Tech, and my lab for the last 18 plus years has studied animals and trying to discover how animals move around in complex environments. This include animals like little lizards swimming in sand, uh, turtles crawling over sand, and more recently, centipedes with many legs scurrying through complex rubble and debris. And as part of being a physicist, we like to do kind of careful measurements on the animals. We call this biological physics or physics of living systems. But we also like to make models of the organisms. And typically, models in physics have come in the form of mathematical models or computational models. In the last 10 years or so, we've realized that we can make what we call robo-physical models, which are basically look like robots, but function as sort of tools that we as physicists can go and poke and prod and see what affects performance of movement, crawling, burrowing, et cetera, et cetera, et cetera. A few years back, a collaborator of mine, who sadly has deceased, Philip Benke, deceased, who was an eminent plant biologist. We were studying similarly how plants would navigate complex subterranean environments. Suggested some of our robo-physical models were starting to actually look like real robots. In other words, they could go into the real world and do useful things. I had not thought of that as a part of my program. In physics, we tend to be pretty focused on kind of more abstract questions. But he had experience in the entrepreneurial space, and we decided to give it a go. And the company started, I guess, we were incorporated in 2022, and Daniel has been with us the entire time. And it's been just a blast to watch as these robo-physical models have transitioned, and now credibly transitioned out of the laboratory, out of the physics lab, and into the real world. And as relevant to this podcast, it's been DYNAMIXEL motors, which we had started using in my lab actually probably around, I was thinking about this, 17, 18 years ago, but they were not up to snuff then. It turned out that DYNAMIXELs were the key to allow us to not only develop precision robo-physical models in the lab as well, but also to kind of start to bring them into more rugged, hardened conditions.
Oh, that's a really, really good thing to hear. We're happy to know that we worked out well enough. I guess to kind of wrap back along to the initiation of this, it sounds like that transition from purely sort of digital models into the robo-physical models that you said might have brought along some interesting insights. Is there anything that you can specifically cite that like sort of the differences, what the benefit of really bringing things out into the physical world for this testing was?
That is an excellent question. Let me field that one too, because it's something which has been, if not an obsession, kind of lingering in the back of our minds now as long as we've been doing it. I will say that I'm not the first to make robots or treat robots as models of living systems. I would say that many of the organismal biologists, including the folks I train with, like Bob Full and others, started using robots by collaborating with roboticists as models going on 20, 30 years ago. Uh, Back then, it was much harder for the average person, including the average experimental physicist, to build a model. So it was just not an option to build a robot as a model. It was just not an easily accessible option. When the motors, like the ROBOTIS motors, came online, the DYNAMIXELs came online, and low-cost microcontrollers and 3D printing, then if you had an idea, if you dreamed an idea, you could build that idea. This, I'd say, is in direct analogy to the proliferation of simulated models, where simulated models 50, 60 years ago was a real challenge. Only a very few could do that. Now, there are plenty of packages which you can make very credible looking animations which allow you to, in principle, model, let's say, a living system if you're interested in locomotion. There's always been the option, at least for the last several hundred years, of doing a mathematical model, an analytic model with pencil and paper. But those techniques are good in very restricted situations and tend to run out of predictive capabilities when things become a little more realistic. In the case where the literally rubber meets the road or the limbs meet the ground, in our world, it started that we simply did not have. We were interested in how animals, like a little lizard, swims in sand, or a turtle crawls over sand, or a sidewinder rattlesnake goes up a sandy incline. The key feature there being that the material can behave like a solid or a fluid and can be very shifty depending on if an organism makes a sudden move or pushes too hard, et cetera, et cetera. And there we simply didn't have analytical pencil and paper type models of the flow of granular material, nor was it particularly efficient to compute the trillions of interactions that grains would experience gliding among themselves with either the organism or the simulated model. So in that case, the robo-physical model was the only game in town where we could have a credible model of the real system. Now, since then, we've made some progress on both the analytic side and the computational. Still, the computational systems are very slow, often in realistic environments, relative to what the robo-physical model can provide. More flexible in certain ways and less flexible in others. So I see this approach as kind of a complementary modeling approach. And it has the nice output of actually producing something in the real world that might look like a real robot to an engineer.
Yeah, that actually makes a lot of sense. I hadn't considered the fact that up until the last 30 or 40 years, even computational models were sort of restrictive. That's something that I think plays very well into the progression of sort of physics modeling, right? You were mentioning analytical models have been around for hundreds of years. That's how we've done
Yep.
things forever. And then it became possible to compute things. And that was in what, 70s ish, where
Well, this,
we were and then physics moved a huge step forward because all of a sudden it was possible for us to simulate huge amounts of environments relatively quickly in a way that we simply couldn't do before. And now you're saying we're going through another revolution where for things which are computationally expensive, like you said, very dynamic situations, fluids, stuff like that, that it wouldn't make sense to simulate an entire pool of water to then simulate this, fish or whatever. Now we
yeah.
can build a robot and just throw it in the water and then see what the robot does.
And that's the interesting thing, right? It's not a either or, right? It's a yes and kind of thing that that all models. There's a famous quote: "All models are wrong. Some models are useful," and I kind of live by that mantra. You know, the robo-physical model, the computational model, or the analytic model are not the. In my case, I'm interested in the living system, but you could be studying a black hole. You could be studying, whatever another condensed matter, or hard condensed matter system, and make a model. They're not the real system, but they can potentially give you insight. And then you have to decide what kind of insight you want. The robo-physical model is great for, let's say, a locomotion study in a complex, like I say, fluid. We're starting to study fluids now too, locomotion of fluids or sand, or even an environment like grass or leaf litter, which we may not have a computational or analytic model. They're great for that. However, they can break. There, you have to have the person who's running them set it up, put it down, repeat it over and over and over. It's real world time consuming. In contrast, the simulation, you can just push a button and overnight back comes some simulated runs. Do you trust those? Do you have a model? Did the simulation take forever to run? If it didn't, and you do get a result, you have access, because we use this all the time, to information which is simply hard to get in a real world. For example, I may want to know when my lizard robot is swimming in sand, the stresses and the stress fields in the grains. I may want to know that, or the flow velocities. that's simply inconvenient or maybe impossible to measure in the real world. But with a calibrated simulation, experimentally validated simulation, you can, in fact, get an estimate, a model of a model, if you will. And so that's how these things in my lab have worked together with the complementary piece that sometimes you just want a plain old analytic model that you can get right a formula for. It cuts off a lot of the computation because you've got an analytic formula that says, I plug this in here, I get that answer here. Or this scales in this particular way. Those are when analytics are very valuable. So it's kind of a complementary approach. But as you correctly point out, it was not possible to do this computationally. Students in my classes now, I teach, dynamical systems, let's say, and we want to solve a differential equation. Right now, you just go into MATLAB or your favorite, numerical package and type ODE45 and you're done. That was like, that wasn't a thing 60 years ago. It was a big process. And I suspect we're heading there with robots too.
Oh yeah, I'm sure we are. We're right on the edge of a very big step up, which I guess sort of semi-related to that. To get back to more of the practical realm, you
Yeah,
mentioned that you guys are transitioning ground control in specific is sort of the spin-off from the lab, with a little bit of
yeah,
a more practical bent. What kind of
right.
specific applications are these applying to, and how has the benefits of your robo-physical models enabled you to conquer those challenges?
Yeah, let me start off very briefly and then I'll let these other guys talk because I could just give a preamble that, you know, this was really an again, I'm not a roboticist by training. I absorbed the robotics from real pioneers and leaders in the field about 20 years ago during my postdoctoral training. And I just sort of wandered into this. It turns out that this physics approach, this physics meets engineering meets, let's say, biology meets applied math, has been quite fruitful, I think, because it really does put an emphasis on real world interactions, which are unavoidable. And that was sort of naturally, we'd say, pre adapted our robots to kind of go into the real world. However, that transition has not been trivial. And I think that luckily I have had in my lab and continue to have incredible folks like Daniel, like Eric, some of whom have transitioned into this commercial space as well. Well, Daniel, why don't you take it away from there? Because I think that you can speak to the use cases. Which again, I also want to plug my collaborator and co-founder Philip Benfeed was the one who really recognized he had an agricultural background, entrepreneurial agricultural background, and he recognized the potential value of these robots in agriculture. So why don't you take it away, Daniel?
Yeah, no, that. Thank you, Dan. And yeah, you gave a very, very thorough kind of background on robophysics, and that's what brought me into the lab in the first time. Like the way that I met Dan, for example, is actually through one of the classes that I was taking at Georgia Tech, where I was taking a Physics 2 class on electromagnetism, and Dan was asked to be a guest lecturer because my typical teacher, my typical professor, had to step out for that day. So I was sitting in the front row with a cane and a broken ACL, and was asking a bunch of questions while we were talking about lightweight electromagnetic waves. And afterwards, I went up to Dan for a couple other questions, and he asked, "So, have you ever considered doing research with, given your these are all very good questions? Have you ever considered kind of doing research and exploring kind of your curiosity?" And I was actively looking at research at that time. And then I looked at his lab, and I was like, "That's a robot zoo. That's awesome." Uh, because I saw robot turtles, robot snakes, robot worms, robot mud skippers. So I've always been passionate about robots, and met Dan then let me join the lab early on, like in the summer of 2017, and I've stuck around with him ever since. He hasn't been able to get rid of me. And then in 2022, when I was graduating from my master's, I was trying to figure out what my next steps were, and that's when Dan told me that he was thinking about doing a commercial venture and was doing that with Philip, and I wanted to join in for the ride. And specifically, one of the points that came around at that around that same time is that a condo in Miami collapsed, and it was a couple blocks away from where my uncle lives. And
Oh,
so one of the big things that I remember from the rescue workers at that time were that they were frustrated with the state of robots at the time, where they were saying we have all these robot dogs, we have all these robots that you see in the media, but they're just walking on top of the rubble. We don't need that. We can do that ourselves. We need something that can go inside of the holes, go in and go where humans strictly cannot. And they mentioned that what would be great is if we had a robotic ferret or a robotic weasel. And so that stood out to me, that that's a kind of limitation in robotics at that time. And with the robots that we were cooking up in the lab, they're based on centipedes. And we had seen promising results, not just on open ground, but also to work in very, very confined spaces and be able to have the form factor of a snake, but still have the locomotion capabilities of a legged thing. And that stood out to me. And so I wanted to join in and joined in around like 2020, late 2022, early 2023. And uh, we finally like managed to secure a grant to get this project going and get this company going, specifically targeted not at search and rescue, because we don't working in search and rescue, we want that to be the end goal. However, it's very difficult to structure a company and a use kind of commercial approach on disaster relief because I mean, we didn't want to be in the mindset of we see disasters on the news and see people like suffering and be like, awesome, all right, this is our chance. We don't want to be in that mindset. Um, and so we actually targeted, like, we took a step back and we noticed that these robots are really made for going in areas that nothing else can go in right now. And how we kind of like to frame it nowadays is it's for the dull, dangerous, and dirty tasks of today.
Ah,
Um,
yes, the 3Ds.
Yes, the 3Ds. And so our first approach is into agriculture, doing weed control and inspection 24/7, running around the field, checking out for any potential diseases, pests, and scaring away critters from the crop. We're also aware that this can be used not just in ag, but for defense and not to carry bombs or carry guns, but for
But
more reconnaissance and kind of surveillance operations. As well, it can be useful for uh, from the field to the battlefield to the at home in the crawl spaces and attics, and even all the way to space. In fact, so it can be used in so many different sectors, and that's I think the really cutting edge like capabilities that ground control robotics is bringing to bear and kind of changing the robotics landscape in a way that I think is very special.
Well, and
I
like,
guess carry on.
well, just as kind of like for you asked about, well, like where do the insights from the lab come into like these particular applications that we're looking at, and sort of our key approach that sets us apart from a lot of other people doing robotics right now is if you have a robot like a quadruped or a biped or a wheeled thing, and you want it to get through a really difficult like a difficult set of obstacles or some difficult terrain, you throw more compute at it. You like more AI and more sensors, more lidar, more like, oh my goodness, like how much money can we spend on like fancy sensors? And the insight that we got from the lab that we published in a science paper a few years back was that you can either, in order to locomote effectively, you can have a few legs and super complicated compute, or you can have what we call like morphological redundancy, a form of like mechanical intelligence, where you have many legs and much simpler compute. And so our robots, because they're long, elongate, and multi-legged, we're able to achieve really robust, what we would say even like theoretically guaranteed locomotion on these super complicated terrains with really minimal sensing, because the intelligence is contained within the mechanical design and not within like AI models or anything like that. And that also makes the technology super generalizable. Like Daniel gave a ton of different use cases, and it's not like, oh shoot, we have to train the AI models so we can work in a crawl space now, or we have to train the AI models so we can do this. It's because all of the intelligence is contained in the mechanics. It makes the technology so generalizable.
I'm not sure if this is something that can be condensed into a format like this, but do you think you could provide a quick explanation of how that sort of scales, how the mechanical redundancy compensates for that computational complexity and gives you more stable gates in that way?
Yeah, let me field that. I'd say honestly, that is an excellent question and one that's of current research interest. So I don't want to say too much because we're actually working on just that right now. The question becomes, you know, if I have we've discovered, this was a paper back in 2023, Bashi Chong, who was a grad student and a postdoc in the lab, and who's will actually be starting his faculty job at Penn State in engineering and probably buying a lot of DYNAMIXEL motors. He came up with a very clever analogy between information theory, communication theory, as it used to be called, and locomotion. With the key insight is that if I want to transmit a signal from A to B, what I do is I generally code it in some way, right? We now know about all sorts of coding schemes which allow us to press and send video, audio, whatever, just like we're talking on now. And one of the coding schemes that can work, albeit slowly, is simply redundancy. Just shout that message over and over and over and over and over, and either average or take, eventually you will get, if your channel is not too noisy, eventually you will get that message through. Maybe slow, but you'll eventually get there. We discovered that, and mathematically we demonstrate this in the paper, that in fact these multi-legs sort of function in some way, analogous, I'm speaking loosely, as a kind of redundancy in message transmission. Instead of calling them bits or binary digits, we call the interactions BACs, basic active contacts. And so if you have a sufficiently redundant BAC coding scheme, we can prove in a mathematical noisy landscape, which again we tested with robophysical experiments, guarantees that your robot will get from A to B in a certain amount of time. That time will depend on morphological features like the robot's legs, this sort of stuff, as well as terrain kind of noisiness, which in this case would, let's say, be rugosity or bumpiness of the surface. But the cool thing is that what it says then is that I can get from A to B with, let's say, in open loop. Now we're talking about an open loop where no computing and sensing is needed, because that's our kind of baseline thing. We think if you can do it in open loop, and you could do it well eventually in open loop, that gives you, and you do experimental work, theoretical work, and scientific work to explore what actually might be a good thing to sense in the environment or in your body and respond to. You can layer in that computational complexity in a more sensible, systematic way. And so it turns out that if you have 4 legs or 6 legs, and you're crossing a noisy landscape in open loop, you might get there very quickly if you happen to just randomly pick a good spot through a noisy, bumpy landscape where where good foot contacts will be probable. You might also things might get really bad. And in fact, we could see that in experiments we do with 4 and 6-legged robots, that sometimes they can make it through our laboratory bumpy landscape quite quickly. Sometimes they go quite slowly. So the variance in how large the range of speeds, let's say the time it would take to get a certain distance, can be high. The beautiful thing is that when you add more and more limbs, what happens is that there's never sort of, on average, a bad contact, speaking very colloquially. And what it does is it shrinks that bound. So you're both pretty good, and well, you could say pretty bad, but you're consistent. You have a predictable time it will take to go in open loop from A to B. And it gets more and more predictable, meaning the bounds get tighter, the more limbs you add. Now, obviously, there's a limit. You don't want to add lots and lots and lots of limbs if you want to guarantee from A to B. And that's where feedback comes in. And that's where computation comes in. The question, though, is what to measure, when to measure it, how often to measure it, et cetera, et cetera, et cetera. And these are, in fact, the questions we are working on right now as I talk.
Oh, that's quite interesting. So I guess to sort of summarize and check my understanding as well as hopefully that of the audience, is that the long and short of it is that when you're working with something with many legs, essentially, if some number of those legs are going to get the right, a stable gait, and if you have enough of those legs getting a stable gait reliably, you can basically guarantee transit times across any environment, stuff like that.
That's one way to put it. Stability is one thing, and effectiveness is the other. And that's why we sort of think of these back patterns. Is there's better and worse ways to generate basic active contact patterns.
Hmm.
And it's an interesting, in the same way that there's a whole industry of figuring out what are good compression schemes, right? If I want to transmit to a satellite, if I want to cross the internet, what are good compression schemes to ensure that the message gets from A to B in a timely way? We think there's a whole universe of interesting, what you call them gates or back pattern schemes, which do better or worse in different classes of noisy environments. This is a part of our research program now. Now, how that relates to the animals, I don't yet know, but that's for me, of course, what it's going to end up coming back to. The practical thing, though, and this is, I'm glad Eric alluded to this, the practical thing was, for me, this was almost like a green light to proceed with this project. We'd seen from a previous postdoc who made it, Yasmin Ozkan, who's a professor at Notre Dame now, who's also probably buying these motors. She had built our first kind of myriapod robots, really as models to the organism, because again, why would you want to add so many redundant motors and so much seeming complexity to your robot, right? Why not just stick with what you like? And what she discovered is she took this thing outside, her little robo-physical models, which were 3D printed with DYNAMIXEL motors, and she just turned it on, and it just kind of went through leaf litter and went through grass and just did so nice. And so that was interesting, and she and Bashi wrote some papers on this. But it was only when Bashi made this analogy, I think, to this that you could guarantee that the thing could go from A to B. I could say, man, you could tell a farmer who has a particularly rocky landscape that this one robot will traverse an acre per day, full stop. In the same way, I can sell you a Roomba, if that were my business. I can sell you a vacuum robot with wheels, because I can tell you that V is omega R. Like I teach in intro physics, that if I rotate at a certain rate and I have a wheel of a certain radius, that's how fast I'll go. And that guarantees that my Roomba will clean my house in 2 hours. So we think we now have that principle, but for robotic systems, and they don't necessarily have to be legged. Basic active contacts can apply to how limbless systems push on the environment, interact with the environment. We think we have that principle that basically lets us then say, okay, you have an environment, we think we have a robot morphology or control scheme for that.
Yeah, I guess to follow up on that, are there any particular environment structures or sort of conditions that either provided surprising results or that are exceptionally difficult above and beyond sort of the average for something like this?
Yeah, I'll let these guys answer because they've been actually going into fields and testing. But I will say that my first foray, before I started in my lab, 2007, in the world of biomechanics, nobody was really looking to speak of at organisms moving in complex terrestrial environments. People had looked at swimming and flying, which were thought to be, the real height of complexity, because you have to, in principle, if you wanted to model this, solve the Navier-Stokes partial differential equations to understand how a bird wing, keeps the thing aloft. It was thought that the terrestrial problems were pretty simple, and that's largely because humans, when we think of terrestriality, we think of paved roads, maybe some stairs, maybe a grade, but that's about it. The world of little critters and bigger critters is replete with now what we call complex pterodynamic interactions. Not aerodynamic or hydrodynamic, but pterodynamic is the word we coined. And those, our first big surprise was actually in granular pterodynamic environments, sand. We discovered, and this was actually with our first robophysical study done with Dan Kodachek's group at UPenn, we discovered that a six-legged cockroach-like robot, shoebox-sized thing with 6 springy C-shaped legs called Rex, which was really good at running over hard ground at multiple body lengths a second. You put it into the average granular material, and using that same way that it was spinning its limbs around, you can look it up on YouTube to see the videos, failed miserably moving in the granular material. Just failed. The same, And then we discovered, this was a former student of mine, Chen Li, who's now a professor at Johns Hopkins, who also uses DYNAMIXELs. Chen discovered that slight tweaks to the timing of those limbs that were circulating around led the robot to either sort of thrash in place at 0 body lengths a second or move at 1 body length a second across the environment, across the grinding material. That was the first big surprise to me. And what that said was, oh man, there's a whole universe of aerodynamic interactions we know precious little about. And boy, is it important to be able to contend with those. That to me was the first thing. And with the granular systems, we've just had surprise after surprise after surprise with these things. And now, these guys can tell you, because of the cool coupling to engineering in the real world, we're starting to go into the real world and see environmental interactions are just like terrifying. Tell them your favorite, Daniel. I know which one it is.
Yeah. Well, the one that is currently being annoying is that was surprisingly annoying is tall grass, and I'm talking grass that is over twice the robot's height. So that we're at a very different scale with this with our devices, and we'll send you videos that you can play right here, but the onboard camera view looks like the footage from Honey, I Shrunk the Kids. That's what it looks like. And so it's a very different world. And so interactions and environments that you typically wouldn't think would be a problem, it becomes a challenge there. Now, we've managed to find strategies to get over that trouble, but that was one of the features where it was like, okay, yeah, we're going great across boulders, through pipes, through all types of different scenarios on flat ground, across stairs. Cool, 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 cool. All right, let's take it across some grass. Okay, it's working fine on this lawn. Let's go into that more bushy area, and then it just started getting hampered. We've been able to figure out strategies thanks to our robo-physical approach and kind of this back and forth between the lab and the company. But that was one that was surprisingly challenged, and it's very different than challenges that you would see for like a robot dog or a robot biped, where you're. I mean, for example, one of the challenges that you would have to face is how to go, how to keep stability on your robot when you're like walking across boulders or unsteady environments. And because stability is the name of the game with those really tall, long-legged locomotors. Because if you fall, then it's very damaging. With ours, the robot, if it falls, it's not really falling because it's already the belly is about like a couple centimeters from the ground, almost. So stability is never the problem on this guy because of the many legs. And so we didn't have any trouble on the boulders or the typical robotic like testing areas. The tall grass one was a surprising challenge. But yeah, was that the one that you were thinking of, Dan? Yeah. Go.
I like that one. You know, it's that those are, you know, that's the environmental side of the world. The other side of the world is, you know, what goes on inside your body. Your body as a robot. You know, how do you arrange your collection? Now you got, I don't know, 30, 40 motors or something in these things. How do you arrange them? How do you control them? How do you couple them? Do you couple them rigidly, or are they elastically coupled? You know, how do limb shapes? All these important, interesting kind of in the bio world we call them neuromechanical, where the control meets the biomechanics. All these things matter, and so it also, the other feature of what's surprising is just how little tweaks in the in the style of actuation lead to big change in performance. And the example I'm thinking of is not a robot that's necessarily being immediately commercialized by GCR, but is one which was the subject of a study published a few years back, in which we were trying to understand how, this I think is a good example, how little worms, little nematode worms, the C. elegans worm, a very famous worm in biology, how they're able to navigate really complex environments, namely rotten fruit, soil, backs of slugs, and sort of thing. And despite having a relatively limited, compared to us, nervous system consisting couple hundred, neurons that could potentially do some computing. And the answer turns out to be, at least partially, in how their body actuation happens. You don't have a sort of traditional, and we got at this by making a robophysical model of the worm. It turns out that it's much larger. It's nearly a meter long, where the worms are kind of a millimeter long. But we also discovered that if you get the kind of dissipation in the environment right, then you can basically scale these things. But it turns out that simply by changing the motor configuration, instead of a kind of serial chain of motors, which what you might sort of do if you were making a wormy-like robot or a snaky-like robot, you array those motors, DYNAMIXEL motors again, on either side of a flexible body, and then you use cables to actuate the next segment up. And there's a wave of kind of cable actuation that runs down the body in a pre-programmed way. And by twiddling the amount of cable winding and unwinding on either side, you can get the robot to either get stuck very easily or make it through a pretty complicated rugose environment with basically open loop control. So that's the other thing, which, by the way, you can in principle model motors wound with inextensible cables on. You can model all that computationally, but it becomes challenging to believe those computational models when the mechanical complexity goes outside of what might be prepackaged in most of the multi-body. So
And I'm sure that speaks to the biggest benefit of robophysical models in general, which is when you're working with even the most accurate simulation. As you mentioned previously, a model is just a model. But with a robophysical model, you get to test it with as close to real world physics as possible, right? In the real world.
And it makes that leap. This is what for me has been the big discovery. And something I never would have predicted. It makes that leap to the real world, to real world applicability, and real world action. Not as because you sort of have solved a lot of the real world problems. In simulation, you can always do something to make it work. You can always do something. You can change. The friction value was 0.6 in the real world, but really, it's point. We can put it at 0.3 here. Oh, yeah, it kind of works. You can always make it work. It's harder to fool nature in the real world.
It's very, very true. Well, I guess we're getting near the end of today's interview, so I wanted to give you guys an opportunity to say, is there anything that you wanted to share with anybody who'd be looking to get into robotics now? Any advice for up-and-coming researchers, developers, anything like that? Imparting wisdom?
I'm going to let these guys start because they're obviously much closer to that stage than I am.
Sure, I'll start. I started working with robots in my high school robotics team back in
Same here.
2014. Yeah.
Same here.
And I've seen more high school robotics teams come by, and I've also seen how much robotics education has started to get into middle schools and like proliferate. The big thing that I would like to always emphasize is be patient, and failure is normal. It is normal for things not to work first time. I can't tell you. It has gotten to the point that if something works right out of the box, I am shocked and I'm skeptical that something went wrong because nothing should work on your first try. But it's always a matter of like failure is normal. It's just always take it with an open mind and take it in stride and learn from each one. And patience 90% of robotics is about patience and being stubborn, and the last 10% is kind of thought and kind of working in the ideation side is what I've heard from past people as well.
Yeah, and I think, yeah, I would add just like the barrier to actually getting into the stuff nowadays is so ridiculously low. Like as we touched on earlier, as Dan said, I mean the proliferation of 3D printers and all that. But now, I mean, you have internet resources to like teach you how to do anything. Like I did high school robotics, and there everything comes to you in like a nice package, and you work with their software, and like everything's you can't really mess anything up. But now, it's so easy to, I don't know, just go out and like buy a Pi or buy servos or anything, like the resources for learning how to use this stuff are so good, and it's gotten so cheap, like comparatively nowadays, that there's like really nothing like stopping anyone. And like the DYNAMIXEL motors in particular have been really essential for the sort of stuff we're doing, because we talk about like the length, like how many motors you have really matters, and the length of these things matter. Well, with like the DYNAMIXEL protocol, you just like daisy chain 2 more motors on, and boom, like you've added another segment. And so there are all these like really thoughtfully designed products like DYNAMIXEL and like other sort of things. I think also that like if once you find them, they can make the robotics process a lot easier. So plug for DYNAMIXEL, like specifically because of this elongate multi-legged stuff. Like this is a perfect form factor servo for this sort of thing.
And also, last point, and then I'll hand it to Dan because he can give many good parting words on this. DYNAMIXEL has been very, very helpful for GCR and to getting involved in robotics at the start. My first project in the lab was using DC motors and doing H-bridge, using H-bridges to control DC motors and doing the PID. I had to learn basic control laws back in my sophomore year of college before they were taught at like the fourth year. And yeah, it is a valuable lesson. However, DYNAMIXEL, it is so easy to get somebody started and get them situated with exploring not just how to run robots, but also with the idea, the mindset of an experimentalist as well of what what does it look like when it's in the world, and what are the interactions, and taking it with taking a scientific taking a scientist point of view to engineering and to robotics. um, DynamixL has been essential. We can bring in somebody new from high school, and just show them like, here's how to run these motors, and within a couple hours or even an hour, they are fine and they're ready to start programming and running these guys. It is incredible what DynamixL has been able to do by lowering the barrier of entry on this guy and these guys.
That's a big part of what we're trying to do. Make it so robotics is as accessible as possible.
I think that's great. I think those are excellent points. It's good for me to hear from these guys because I didn't have high school robotics. I'm old enough that wasn't a thing, and maybe my high school wasn't good enough. And so now I see the students who I'm in physics department, right? But at Georgia Tech, which is a premier engineering place, and so we get just incredibly capable students, and they now come flooding into my lab, and like Daniel says, you give them a little project, and off they go. And the creativity, that's what I like about what is building. They don't have to worry about programming a controller on everyone. And I'll tell every time they try something, and again, I'll reiterate that for me this is very nice and nice to be chatting with you, because I remember we were building a sand swimming robot. This is one of our first robo-physical models, before we called them robo-physical models. And this was, I don't know, 2008, something like that, 2009. And we were using a certain kind of servos, which were really strong and powerful. And I think we probably used Arduino. I can't remember how we controlled them, but it worked okay. But we wanted a little bit smarter controller in there. And okay, I had to go back and program it. It was harder to access. And then, as the guys are saying, chaining these things together so that power didn't drop out and all this stuff. I just remember the PhD student Ryan Matlin doing this. And then somebody brought in a DynamixEL, and we tried it, and it immediately failed. Those at that time, they weren't strong enough to move a robot through a granular material. It happened to be granular material, 6 millimeter plastic particles, because that's what we were using at the time as our model grant too. So we gave up on DynamixELs, right, for a while, for a couple of years. And then somehow, and I don't know who it was, somebody started bringing in some of the ones, I think maybe around 2012, 13, something like this. And since then, they're just now, we can't order enough of them, particularly with the company now.
Good problem.
Literally. Literally.
Yeah. Well, is there anything that you guys want to share with the audience before we head on out for the day? Social media, links, anything like that?
I would make a plug for I want to say there's something very important that I think that has to be said, that all the work that we've done in my lab and all the work that a good chunk of the work that's being done in the company even today is done on the back of funding by the federal federal government. This is a very important thing. National Science Foundation, Defense Department has been extraordinarily kind to me and people like me in giving out grants, funding, with basically no strings attached. To say, yeah, go discover amazing, cool things. And in fact, the DYNAMIXEL are a critical part of why we can discover these things in the rural physical world. So, the funding sources for this, which have largely been public, are an absolute critical piece to this. And I just want to make sure that gets put into this podcast. On the other side, is that if you're a student out there or someone who's interested in this world of robotics is an incredibly interesting discipline, in part because I think it combines so many disciplines. Interdisciplinary is a word people like to use. And historically, physics has not been part of the gang. But I think that there's increasing recognition by physicists and among roboticists that there are incredibly important physics principles to both learn and apply to making robots really take off and move out of the lab and into the rather factories in the real world. So those are my sort of parting thoughts, if I may.
And you can always check out groundcontrolrobotics.com. You can find us on YouTube, LinkedIn, Instagram, Facebook.
And of course, those are all going to be in the description down below.
Yep.
Awesome. Thank you for having us, Jonathan.